Good afternoon, everyone. I don't have many announcements. It's just a quiz that will be released hopefully soon. So if there are no questions, I can just jump into the lecture. Okay. Great. So okay, so to remind everyone where we are, we're talking about I/O devices and I/O subsystem. We now want to see how the operating system can communicate with the device controllers. So the last topic that we discussed in the previous lecture was the two common ways to communicate with the device controller. So the controller has some registers inside, some buffers, and somehow we want to communicate with the controller. We want to read or write to those registers and to those buffers. One way to do this is to just have a separate, isolated address bus that connects the I/O devices to the processor. And if the processor wants to talk to the devices, it can just assign addresses to those devices. Everybody knows their addresses. Here in this context would be ports. And then whenever the operating system, the processor wants to read or write from those, it would just use a separate set of instructions like the ones that we talked about in Intel. They're like in and out instructions. Compare them with store, load and store. So whenever you use these instructions, the architecture knows that it has to use the separate I/O bus. Whereas if you, instead of out, use store, the architecture knows that it has to use the bus that connects the CPU to the memory to communicate with the memory instead of I/O. The other way to do this is memory mapped I/O. In this one, I/O devices and the memory, they all share the same address bus. So the processor executes normal loads and stores. Both the I/O devices and the memory are listening to the same bus. Each one knows which range of addresses are assigned to them. So that's how they know if a load or a store is targeted to them. Here is an example. Let's say that we have a memory mapped display controller. And let's say that our controller has, just for the sake of an example, two registers, a status register and a command register. And it also needs two buffers, graphics command queue and a display memory. So in this one, here we want to see an example where we're communicating with the display through memory mapped method and style. So what happens is that during the boot time, you usually communicate with the device, and either the BIOS or the operating system assigns the ranges to the device, so the device knows what addresses it has to listen to or write to. So let's say that we want to, change an image on the screen, what we could do is, we can use the range that is specified here. So the display memory, basically whatever is in it from this address to this address, whatever we write to this, the display will read and display. Let's say we want to, send some commands to change the picture somehow, like we want to write set of triangles that describes some scene. We can now use the graphic command queue to send some commands saying that for this triangle, change it to this triangle, for this triangle, change it to that triangle. So that's sort of what this could be used for. So we can just use our store command to write to this queue, and when we write to this queue, the hardware controller knows that this range is allocated to it, so it will just copy them into its internal buffers and then basically executes those commands. And then here is an example where we can use those command registers, compare them with the graphic command queue. Here is basically you're just sending one, for instance, one command to render the triangles, or to shut it down, or to refresh the page, something along those lines. You can just write to the command register, and then the controller will react to that command, and then you can just set check the status to see what's going on, if the display is doing what's supposed to do. You can use the address translation if both of the I/O devices and your memory are on the same address bus. You can definitely do all the translations that you want, so that you have also protection. Okay, I got a question here. Are the addresses of these registers in the controller virtual addresses? Okay, that's a good question. If you don't get an answer for that question in the few coming slides, ask it again. I'm going to address that concern. So let's this is a recall on, now that we know how to communicate with the devices, where the memory mapping happens, how can we transfer data between the processor and the devices? The first one that we saw actually in early lectures was programmed I/O. So basically in this one, the CPU is involved in sending and receiving every single byte. It's simple hardware, but it consumes a lot of CPU cycles. The second one that we talked about was direct memory access, where you just communicate with the controller. You give it some addresses, and then the CPU starts doing other stuff. The controller transfers data from or to memory, and once it's done, it raises an interrupt telling the processor that the data is ready. We talked about how it's done. Now, let's look at it in the context of PCIe devices. It's kind of like more intuitive in this context. It's a little bit different than how it's done in other communication protocols like ISA. So in older communication buses, you usually would get a dedicated DMA controller on your chip that would basically manage all the DMAs. Now with PCIe, there is no need to have a centralized DMA controller per se. Each device can, as we said, PCIe provides a very similar networking experience that you have with, your usual networks, switch-based networks. So there is a possibility for each endpoint to communicate with any other endpoints on the PCIe bus. One of the endpoints on the bus is the memory. So each device can directly send messages to the memory. And that's where the DMA could become easier without any centralized DMA unit. Each device could have their own DMA engine, usually proprietary DMA engines that each device implements their own engine. So all you do is that you tell your device to write write a bunch of data to memory, and then your device, basically the DMA engine inside your device, will start talking directly to the memory and writes and reads data to and from memory. And once it's done, it just raises an interrupt saying that the transfer has been finished. Now, what about memory protection? So here's where the question that was raised should hopefully get an answer. So typically, I/O devices can only read and write from a contiguous range of memory addresses. If you remember when I was talking about PCIe registers, one of the ones that I mentioned was the base address register, where at the beginning it has only it basically tells the system how much memory this device needs. And then assuming that it gets that memory allocated to it contiguously, once the memory is allocated, the operating system or the BIOS writes to this register the base of the address, the base address in memory that the contiguous space starts. In old computers, usually I/O devices could directly access physical memory, as I mentioned. And in those cases, your device uses physical addresses to communicate with the memory. The same with the device driver, usually communicating with the device using physical addresses. It was fast because you don't need to translate anything, right? There is no address translation. We saw how dramatically it could add overhead, just having to translate addresses. So it was fast, but then the problem with it is that it's just not secure enough and not reliable enough. If you have devices that you don't necessarily trust, then you have a problem. Now, the other downside of this method is that it just is not that flexible, because the operating system has to, allocate contiguous ranges of its physical memory to all devices. And you could imagine if you have a lot of these devices, then you could potentially get into, fragmentation issues and all of the problems that come with it, because you have to basically allocate contiguous pages to each device. So new devices, new architectures provide address translation for I/O devices. This is what you usually get these days in your system. So if you remember, we had the memory management unit that was sitting between the CPU and the memory right before the memory hub. Whatever comes out of the CPU would go to this memory management unit, get translated to physical address, and then would go to the memory hub and do the memory to get an answer. So this is our usual virtual to physical address translation that we saw in the previous lectures. Now that we have the I/O hub, where all of our devices are connected to, we can do the same thing. We can just put an IOMMU, I/O memory management unit, the same concepts, really nothing different. So everything that comes out of your devices gets translated here. You can actually check and make sure that devices are accessing what they're supposed to. It also allows the operating system to potentially allocate non-contiguous physical addresses to your devices. So from the device's point of view, it's just a contiguous virtual address, which is fine, but then that gets translated to different regions of memory. So that gives flexibility to the operating system's operations. It definitely adds some overhead. And in some cases, you may decide not to use IOMMU. You just disable it. Just go with the physical address translation if you have like an embedded system or yeah, a real-time system. You might just bypass this. The same with CPU. So if you're running a device driver, your device driver just communicates with the devices using virtual addresses. Okay. Now things get a little bit complicated when you're concerned with PCIe devices when you want to do memory translation, and that comes from the way that the PCIe packets are handled. The first problem that you have with it is that the way PCIe protocol is implemented allows devices to bypass IOMMU. So this is because the ones who implemented PCIe or designed the protocol wanted performance. So what is offered in PCIe protocol is something called Address Translation Services, ATS. What it does is it's kind of like TLB. So we had TLB, right? Where you could cache the translated addresses. The problem here is that you can't have a TLB for I/O devices. So each I/O device could have its own TLB. So they could have their own caches to translate addresses and then cache them. And then they just set a flag saying whenever they send a packet with an address, they could say, oh, I have already translated this and I know the physical address. I don't need to go through IOMMU anymore because I have the address. So let me just talk to the memory directly. And the protocol allows this, trusting the devices. So this is just a notion of trust. If you have trusted devices, you could make this enabled, and that gives you performance because you have already translated addresses, and you can just directly talk to memory. But if you have devices from third-party producers that you do not necessarily trust, then you're taking a risk if you let this be enabled. The other problem that you have with PCIe is that the IOMMU resides at the highest level of the network. So basically the root complex, if you go back to the slides where I had the endpoints, so the root complex is where the IMO could be placed on top. If devices want to talk to each other, they may not even get to the root complex. And PCIe allows direct communications. So it could well be that your devices start messing up with each other. If you have, a malicious device, then that device could compromise other devices without even needing to translate addresses going to IOMMU. Fortunately, there is a solution for both problems provided to us by, again, PCIe protocol. You can use a service called access control services, and if you make this enabled in your system, then that by default disables ATS. So basically, it doesn't allow devices to cache translations. And it also, the other good thing that it does is that it prevents peer-to-peer communications and translations. So it requires all packets to come all the way to the root complex before they are routed back to any other devices. So even though you don't need to, if you make access control services enabled, then all packets have to come and go through IOMMU. And that is a perfect solution for both of these problems that I just pointed out. Okay, so now moving forward, let's talk a little bit about I/O performance, and starting with some, concepts and definitions. The first one is latency, which corresponds to response time that we've seen. Basically, the time that it takes to service an I/O request, we're going to call it latency. So from when a request comes to be placed in the queue, let's say here we're just focusing on requests that are initiated by the device driver. So they're placed in this queue. I'm a little bit hand shaky here. In reality, you have multiple queues. One might be in the memory, one might be inside the device. Let's just put them all together, one queue here for the sake of simplicity. Of course, you could actually have queues before the device driver where the system call interface gets the requests from applications, puts them in a queue for the device driver, then the device driver gets them. So this is what I'm saying is it's just a simple simplified version where we're just focusing on the requests being initiated by the device driver and put in a queue, where then the I/O controller and the device will dequeue requests. So the requests are dequeued by the I/O controller and will be sent to the device for being processed. And once the processing is done, then the data is transferred. So all of this is what we're concerned. Now, latency is basically from when the request is placed in this queue all the way until it's processed and its data has been placed wherever it has to go. So if we have to, write back in the memory, or if we have to send it to the network, like if it is, we're transmitting packets to the internet. So whatever that be, that would be the latency. Now the throughput is basically the rate of servicing I/O requests. If we want to measure the highest possible throughput, this point is a little bit important. Pay attention to this one. So if you really want to see what is your device's highest throughput, you basically want this queue to always be full, because when this when this queue is empty, your controller is not gonna dequeue anything. So basically, it's gonna be idle, and that means that your throughput is going to go down. So if you want to really measure the highest possible throughput of your system, you want this queue to always be full. Got a question. So are we talking about the CPU initiating a request or the device? Yeah, so the device driver is running on the CPU. So here, basically, when I have the device driver, this is the program running on CPU, initiating a request, putting it in on a queue, and then the IO controller is going to dequeue from this and process those requests. One example is like send this packet to Google, to www.google.com. Or another one would be display this image on the display. So these are the types of things that we're talking about. It could also be that, oh, read this piece of file, and from this byte to this byte. So that would be your request, and then it goes to your hard disk or SSD, and then the data is transferred back to the memory. So these are the different types of requests with I/O. Now, okay, hopefully that makes sense about how to measure the highest possible throughput. Then we're going to talk about overhead. So the overhead is basically the time to initiate data transfer. So everything. So if you look at latency is from here all the way through data is transferred, we're done. With overhead, we're just concerned about the time that it takes until we initiate this data transfer. So the time that you spend in the queue, the time you spend inside the I/O controller and the device until the data is ready to be transferred. Got another question. So where is the queue? Good question. As I mentioned, this is a simplified version. You could assume that there is only one queue in the memory that the device driver is putting the requests in, and then the I/O controller is just reading from that queue in the memory to see what requests you have. In reality, it could be that the I/O controller will copy the data into its own buffers, and then from within the buffers, the device starts dequeuing. But for simplicity, let's assume that there is only one queue that all the requests are going, and then the I/O controller can read from. Good questions. Okay. The peak bandwidth is basically the maximum rate of data transfer. It would depend on mostly two things. One is the bus bandwidth, the connection. Basically, if you have a PCIe, for instance, version 5, you can transfer all the way to 3.93 gigabyte per second per lane. If you have other types of buses that would so basically that they would dictate what's the maximum rate at which they can transfer data. That's the first one. The second one is what is the device's bandwidth? How fast your device could process requests and initiate transfers. So for instance, if you have rotational disks, basically the magnetic disks, the speed of the rotations would dictate how fast you can transfer data, because the disks should rotate so that the head could, I mean, we're going to talk about it in more details, but there are physical constraints that would dictate how fast you can transfer data. Or if you're, if you're dealing with a SSD, how fast you can read or write from each flash page inside your device. So whichever is the bottleneck would dictate what's the maximum rate. If you have really fast devices, but then low capacity connections, then your bus basically is the bottleneck. If you have really fast buses like PCIe, but then you connect it to a slow device, then your device will be the bottleneck. As a result, because in some cases we can't reach the peak bandwidth of our system, whatever that be. So we're going to focus on effective bandwidth, which basically is the rate of data transfer for an I/O request. And what is that exactly? So the latency is what degrades bandwidth, and latency is usually linear as a function of the size of the data that wants to be transferred. So if you want to, for instance, transfer n bytes, you have to pay this overhead, which is basically the time you spend in the queue, the time you spend inside the I/O device, the device controller, whatever. So there is an overhead that you have to pay until you initiate the transfer. Once you initiate the transfer, from there, you're going to just transfer n bytes divided by your peak bandwidth. So from here on, you're going to just utilize your peak bandwidth, but you have to pay this price before initiating it. So that would be your latency. Now, effective bandwidth is basically how long it takes to send this n bits from the beginning when the request was initiated. So you're sending n bits divided by the latency of this n bits. So if you can see, if overhead is 0, then effective bandwidth equals peak bandwidth. But if overhead starts increasing, then effective bandwidth becomes definitely less than your effective bandwidth, your peak bandwidth. Now, how does overhead affect effective bandwidth? Let's look at an example. So, okay, yeah. Sorry. As I said, this is the formula we have for latency. Overhead plus the number of bytes that we're transferring divided by peak bandwidth. And if you just put everything into a formula, you're sending n bits divided by latency. I'm just refactoring everything. And this is what I get. So effective bandwidth is peak bandwidth divided by peak bandwidth times overhead divided by n plus 1. Now, using this formula, how can effective bandwidth be half of peak bandwidth? So you can just say, I want this formula to be p divided by 2, and then solve for n. You'll realize that if that's the case, then n should be overhead times. Okay, so this is a typo. It should be p. So overhead times peak bandwidth. Sorry about that. So basically, we solved for n, and this is the formula we got. So if you're transferring overhead times peak bandwidth, number of bytes, then your effective bandwidth becomes half of your peak bandwidth. Now, what does that really mean? Let's say that your peak bandwidth is 1 gigabit per second. If the overhead is 1 millisecond, then you need to send 125,000 bytes to just get to half of your peak bandwidth. And if you want to utilize more, then you have to send more. Now, if you have a slower system where the overhead is 10 milliseconds, then you have to send 1,250,000 bytes to just get to half of your peak bandwidth. And if you want to reach higher bandwidth, you have to increase the number of bytes that you're transferring. So here is how you can see the effect. Basically, the higher the overhead is, the bigger chunk of data you need to send to make up for the overhead. Because the overhead is basically the time that your link is going to be sort of idle. You're not using the link. You're just prepping it to send the data. And then you start sending the data. At that point, you start utilizing your link, but you have wasted the overhead amount of time. So to make up for that, you need to send a bigger chunk so that you can mask the overhead portion. So that's the takeaway. Now, what are the contributing factors to overhead? If you look at this figure, we'll see that overhead is basically the time a request spends inside the queue, and then the time that the request spends inside the controller, and after that in the device. So let's focus on this wait time in queue. Let's focus on this queue. Here is a graph showing a kind of like a strange behavior that you usually see in systems like this, where you have a queue. So in this figure, to understand it, on the x-axis I have the utilization, which I'm going to define as the percentage of maximum possible throughput. If you remember what I said when I was talking about throughput, I mentioned that if you want to measure the maximum throughput of your device, this queue has to be always full. Because if you have idle time, if you have times where this queue is not full, then your IO device is not processing anything. So basically, it's kind of like a time where you're idle. And if I add that time into my equations when I'm measuring throughput, that would degrade my throughput, because it would be a time where no request is being served, but I'm spending that time. So to measure the maximum throughput of my system, I need this queue to be almost full all the time. Now, this is what it shows you. So this is basically how utilized this queue is. So let's say 0% means that there is no request in the queue. And then 100% means that the queue is always full. And anything in between has a meaning accordingly. So if it is 50%, that means that 50% of the time the queue is full, 50% of the time the queue is not full. Now, here on the y-axis, I have the wait time in the queue, and that is how long each request, on average, spends time waiting until it becomes the head of the queue and gets dequeued. So what is the time that, on average, each request spends waiting in this queue? Now, this is usually what you see. This is just empirical result. We'll now look at why this happens through mathematical analysis, but let's digest this. Usually when the queue is low load, your wait time in the queue is very low. Actually, if it is 0, actually it has to actually start from 0. But then as the utilization goes up and up, up, the time that you spend in the queue goes up exponentially. So usually if you want to get 100% utilization, you end up spending a lot of time in the queue. So your queue becomes basically backlogged. And each request spends a lot of time in it. Now let's see why that happens. Why this is the way it is. It sort of makes sense. It's intuitive with our experiences with systems. Now let's just look at it mathematically and see what we can get. To do so, let's just look at this problem in the context of queuing theory. Let's just abstract away everything. Let's say we have arrivals, we have a queue, we have a server, and then you have departures. A little bit anal about this. They're not aligned. There we go. I still don't think it's annoying. Great. Okay, sorry. Okay, so let's consider a very simple deterministic world where you have one arrival every TA time units. And then let's assume that each request takes TS time units to be processed inside the server, and then they depart from the server. And at this point, we're not going to care about what happens after they depart. All we care about is from when they arrive until they're out of the server. So what is the service rate? The service rate is the inverse of service time. So if it takes 2 seconds for each request to be served, then our service rate is half requests per second. And then the same with arrival rate is the inverse of inner arrival time. So if you get one request every 4 seconds, that would be your arrival rate, 1 divided by 4. Then you can define utilization of your queue, which is basically the minimum of 1 and lambda divided by mu, which sort of makes sense. The utilization cannot be more than 1. Now, thinking about utilization, if let's say you get one request every 4 seconds, and each request spends 2 seconds to be processed, then we're going to say the utilization is 2 divided by 4, which is half. So this basically means how long, on average, your system, the queue and the server, are idle. Sorry, are working. So every 4 seconds, your server gets to work for 2 seconds. So it's utilized 2 divided by 4. So this utilization is not your queue's utilization, it's your entire system's utilization. And then the throughput basically is the minimum of mu and lambda, because you might have, very fast service time, let's say 2 seconds per request. But if you get one request every 10 seconds, then most of the time you're idle. So your throughput becomes exactly your service time. It becomes the minimum of the two. It becomes one request every 10 seconds, because that's your arrival rate. Now, at any given time t, we're still in that deterministic world where inter-arrival times are deterministic, and then service time is also deterministic. Let's say we're at time t. How many arrivals have we had? All we have to do is to multiply t by our arrival rate. So that would be how many arrivals we've had so far at time t. We can do the same thing with the departures. At time t, the departures is basically t times the throughput of the system, which would be t times minimum, lambda, and mu. Now, how many requests do we have in the queue? Well, the answer to that is our arrivals minus our departures. That's basically very obvious. That's how many people are now waiting. You can definitely see that. So before that, we also want to introduce WT, which is basically the time that each request spends in the queue waiting, and that would be basically your the number of requests in the queue divided by service rate. That's how much your wait time is. Because if you come into a system that has L requests waiting in the queue, well, each one of those requests is going to be serviced by the service time. So each one of them is going to get 1 divided by service time rate. So, sorry, 1 times service time. I'm sorry. So each request is going to take 1 service, and you have L of them. So it would be L times TS. TS is 1 divided by mu. So that's how you get LT divided by mu. That would be the wait time at time t. Now, what happens if lambda is less than mu? Basically, what happens if your arrival rate is less than your service rate? In that case, this minimum becomes your alpha, and LT becomes 0, and WT becomes 0. Basically makes sense, right? So if you get arrivals every 10 seconds and each one of them takes 2 seconds to be processed, then nobody's in the queue. The first arrival comes, spends TS, and then system is empty. The second arrival comes, gets TS, system is empty, so on and so forth. So LT equals WT equals 0. What if that's not the case? What if your arrival rate is more than your service rate? So you get 1 request every second, but then each request takes 2 seconds to be processed. In that case, this minimum becomes mu this time. So your LT becomes T times lambda minus mu. And then your WT is basically LT divided by mu. And that would be T times your utilization minus 1. And this is how it looks like. So you're going to get arrivals at a higher rate of your departures. So this is your departure. Again, we're looking at a deterministic world where you get the time for service is fixed, and the inner arrival times are also fixed and deterministic. So at any given time, this is going to be the number of arrivals, T times lambda, and then T times mu is the departures. So basically this area here is going to be your LT, how many tasks are waiting. And then a task arriving at time T, it takes it WT to be processed. So this is LT and this is WT. And as you can see, as this T goes on, both of these two increase. So LT would increase, like look at here, this is LT and this is WT. And here, this is LT and this is WT. So in this system, basically what happens is that your queue will increase and increase and increase linearly as time passes by. Here is almost the same setting. Instead of one arrival, let's say every X number of time, X unit of time, let's say all the arrivals, let's say 5 of them arrive at the same time, but then it takes 5x time for the next burst. So still we're keeping our arrival rate the same as before. It's just all the arrivals come at the same time, some of them, and then we spend some time, nothing in the system, and again, bunch of arrivals, and then again, we wait, and so on and so forth. Let's see what happens in that setting. So here's like the just a graphical demonstration. Let's say the first arrival comes at this time. It spends some constant time in the server being served. Let's say the second comes at this point, the third comes at this point, and the fourth comes at this point. So they all wait in the queue until the first one is served. Then the second one will come and be served. The third one and the fourth one will wait. Then the third one will be served, and eventually the the fourth one will be served. So as you can see, the service time is the same for all of them. The difference is just they all came almost at the same time at the beginning. And then it takes some time, again, the same process repeats. So in this scenario where we don't have one arrival every interval, we have a bunch of them, it's a bursty world, you start getting, instead of 0 time that we had in the previous model, you start getting some wait time for them. Although your utilization is still less than 1, you get some wait time. So now let's make this a little bit more advanced. How can we really model this burstiness, which usually happens actually in real systems? You don't really get one request every fixed interval. You could get like bunch of customers getting into your shop at the same time. So you have this burstiness in your environment. How can you model that? One way to model this is using probabilistic models and probability distributions to model the inner arrival times. Instead of getting that inner arrival time fixed and constant, we can let it be a random variable, how long it takes. So if I get an arrival at time t, how long should I wait for a next arrival to come? I can define that as a variable, as a random variable. So sometimes it's 0, right away another customer comes. Sometimes it's 10 seconds, sometimes it's 5 seconds. And then I can define a distribution. What is the probability that it takes 10 seconds for the next arrival to come? What's the probability that it takes 20 seconds for the next arrival to come? What's the probability that it takes 1 second for the next arrival to come? A very popular choice for a distribution to explain inter-arrival time is the exponential distribution. So the cumulative distribution function, CDF, for a exponential distribution is defined to be the probability that TA, basically, if you remember, we're going to now model TA. TA was the inter-arrival time between two consecutive requests. So the probability that that time, which is now a random variable, is less than x if you have a exponential distribution would be 1 minus E2 minus lambda times x. So this, for any x more than 0, is defined. And if you have such a distribution, then you can say the expected value, or the mean, or the average inter-arrival time, so the average of TA, is, as before, 1 divided by lambda. So we actually go from this. So we say we want the average TA to be 1 divided by lambda. Therefore, this should be the probability distribution. Now, if you look at the graph here, I have on the x-axis, I have different x's for this formula that I have here. I guess this is probability distribution. Yeah. Sorry, this graph is not this one. This graph is the PDF. It's not the CDF. I'll explain. So the difference, CDF is basically the probability that this is less than this. PDF is basically sort of, not exactly, is a point-wise probability. So again, it's not completely correct what I'm saying, but for those of you who don't know much about probability theory, it would be an identification, this function, of how likely it is for your TA, for the time interval, to be let's say 0, or to be 1, or to be 2, or so on and so forth. So this basically is kind of like what is the likelihood of TA being this particular point. So that's probability density. It's how the probability is it's kind of like a histogram of the probability for different x's. And I have here for different, different averages, I have this graph. Now, what you can see here is that if x is a small, so for bursty arrivals, you want the time between arrivals to be small. So the first one comes and then immediately the second one comes. This basically models that for us, because the probability that TA is small is pretty high. And then the probability that TA is large and big is small. So this basically is kind of like a histogram. It says as x increases, the probability of seeing long intervals decreases, and the probability of seeing short intervals is high, which is basically what we wanted. We wanted to model the burstiness, and this basically does that for us. One property of exponential distribution is the likelihood of a new arrival. If you have exponential distribution, is independent of the time that you have waited since the last one. So in a mathematical language, the probability that TA is more than t plus s. So let's say you have waited so far for s time. You want to see how probable it is that you have to wait another t on top of the s that you have waited. So given that you have already waited for s, what's the probability that TA is more than t plus s? This probability is exactly the same as if you haven't waited at all. So as if s is 0. So as if you want to just see what is the probability of TA being more than t. So it's memoryless. It doesn't matter how much you have waited so far. The probability that you will wait for another t units of time is the same as had you waited 2 seconds or 10 seconds or 20 seconds. So the probability doesn't change. It's memoryless. So basically the past doesn't tell us anything about the future. Many complex systems can be described by memoryless property, but then there are also systems that cannot be described by memoryless distributions. For instance, if you haven't been able to load the page that you're looking for in 5 seconds, then the probability that you will have to wait another 5 seconds is a lot. So sometimes past experiences tell us something about future. So if, for instance, for buses, let's say you have waited 10 minutes so far, or let's say you have waited 20 minutes and the bus hasn't come, it actually tells you that you probably will have to wait another hour. There is something wrong, right? So it's not the case always that you can describe everything with memoryless property. But usually memoryless property is something that we want to have. Okay, I'm going to pause here for 2 minutes. Let's take a break and then I'll continue. Okay, we're back. Okay, let's keep going. All right. So I'm going to actually move on a little bit faster here. If you have a random variable, then you can measure the average of that random variable. So we're going to define m of x to be the expected value of that variable x, which we'll define on a range. Let's say our random variable takes values from x1 to x2. if we have this probability that that X happens, this is for just discrete random variables. If you have continuous random variables, then you'll use integral from x1 to x2, the probability that that X happens times the value of that X. And then you can also define the variance or standard deviation to be the probability. So again, on the range of x1 to x2, probability that that particular X happens times X minus the should be m of x. So there was another one here. Apologies. Yes, so basically x minus x minus the average to the power of 2. And if you just do the math, this whole formula will turn to be expected value of x2 minus expected value of x 2. So these two are different, right? So this is the expected value of basically the power 2 of your random variable minus the average of your random variable to the power of 2. And this base sort of shows you what variance is. In the red one, this is kind of like a histogram of the values and the frequency. So on the x-axis, you have different values that your random variable can get. On the y-axis is how frequent that happened, how frequently that happened. So this dotted line here is the average, which is the case for both distributions, both of these histograms. The average is here, 100, but then the red histogram has a low variance. So all the instances that you've seen are very close to this 100. They're basically from 60 to 120. Whereas this blue histogram, the instances that you've seen range from less than 0 to more than 230. So the variance is higher. So in this case, the standard deviation of the red histogram is 10, whereas the standard deviation of the blue histogram is 50. We can also define a squared coefficient of variance for our random variable. Don't let the name scare you. It's basically the variance divided by mean to 2. So the square root, your average to the power of 2. Now, if you have a memoryless or exponential distribution, then C is 1. You can check. The reason that C is 1 is that your variance becomes exactly the mx to 2. So C becomes 1. If you have no variance, if you have a deterministic system, there is no variance. If variance is 0, then C is 0. So, excuse me. That was weird. Okay. Now, that was background. Let's talk about Little's law. This is a very old law from 1961. Basically, it describes a stationary system. What do I mean by a stationary system? I mean a system where its parameters do not change over time. So if you have an arrival rate and a service rate, they don't change. So all of a sudden, your arrival rate doesn't go up or down, or your service time doesn't change. So if you have a system where its parameters do not change, then you can describe the number of requests or customers in your systems or items in your system, the number of things in your system, that would be L, equal to the rate, your arrival rate, times the time that each item spends in your system. It's quite intuitive. So if each item spends W time in your system, and you get one item per some number of time, so this is your rate, then if you multiply these two, this should give you how many agents are in your system. So I'm not going to actually spend time proving this. You can definitely prove it for a stationary system. But let's look at this in the context of queues. So when you have a queue, you can see that the number of agents that are in your system is basically the number of requests, the number of requests in your system is basically the number of requests that are waiting in your queue plus your utilization, your throughput. This utilization says on average how many agents are being served, right? So that's where the average comes in. The average number of people in your system is the average number of people or items in your queue plus the average number of agents that are being served. So that would be your L. What about your W? Your waiting time is going to be the waiting time that your requests will see waiting in the queue plus the time that they spend in the server, which is 1 divided by mu. Now, use the little law, L equals W times arrival rate, lambda. So basically what you will get is lambda, so this utilization goes away with this one because lambda divided by mu is basically utilization. So this row here will be factored out or cancel out with lambda divided by mu. So what you will get is that LQ equals your arrival rate times your wait time in the queue. So now everything becomes like just focusing on this queue. So if we just focus on the queue, we can say the length of this queue, the average length of the queue, is equal to your arrival rate time times the average time that each item spends in your queue. So let's assume that the system is stable and stationary. So by stationary, I've described what I meant. So your parameters are not changing. Now with the stable, I mean let's say your length, the length of your queue is not exponentially increasing. So basically, you've got to a stable setting where the system is not going to go to an unstable setting where you start dropping your requests or the length of your queue is exponentially increasing. Your system is stable. In that setting, let's assume that the time between your successive arrivals is a random and a memory-less random variable. And let's define, now we're distancing ourselves from that very simple deterministic model. Now we're saying, let's say that the arrival times are random variables. So the arrival rate becomes now 1 divided by expected value of TA, because now TAs are not fixed, so they're random, but I can get their average and then define my arrival rate. The same thing with the service. We can say, okay, our service time is also random. We're not going to spend exactly the same time for every request. Each request may take different times, but let's say we have the average, and that way we can define our service rate. Let's define CS as the SCV of a service time, as was defined in previous slides. And let's say the rho is the utilization of our system, basically lambda divided by mu. Now, as before, define WQ as the average time you spend in the queue, and LQ to be average length of your queue, which is defined as lambda times WQ. Here, there should be a Q typo. Here is the meat of this slide. Basically, I'm here presenting two important cases. The first one is what happens if you have memory-less service time as well. So for both of these two cases, I have assumed memory-less arrival time. That's basically the first M letter in both of them. Now, in the first one, I also assume that the service time is also memory-less. And there is only one server. So memory-less arrival time, memory-less. This M is actually not memory-less, it's something else. But as a coincidence, it just turned out to be applicable to memory-less as well. So memory-less service time, memory-less arrival time, memory-less service time, and only one queue. Then you can have a closed form formula for your WQ. So your WQ in this case is rho divided by mu times 1 minus rho. And in a general service time where you are not assuming any distribution for your service time, so mg, this is general distribution, and only one server, then WQ equals rho times CS now plus 1 divided by 2 mu 1 minus rho. Now, one thing is, if you have a memory-less, this G is general, right? So a specific case of this general case is if the distribution is memory-less. So if you have memory-less distribution and you want to use this formula, if you remember, C of a memory-less variable was 1. So then it becomes rho times 1 plus 1, that is 2, divided by 2 mu 1 minus rho. And then you can just factor out or cancel out these two, and you get the same formula you got with MM1. So this MG1 formula will reduce to MM1 formula if the distribution is memoryless, obviously. And now let's go back to where we started and see if we can mathematically now describe what is going on in this formula. If you see here, rho or your utilization is showing up in the denominator of both of these formula. And as this denominator goes to 0, you can see that the wait time will go to infinity. So that's what describes this situation. So as rho goes to 1, this 1, sorry, I said it vice versa. So as rho goes to 1, so as your utilization goes up, 1 minus rho becomes 0. So this WQ goes to infinity in both cases. And that basically describes why this tend to be the way it is. So to dig a little bit deeper, if you're not satisfied with the formula, you're like, okay, formula describes it, but why in reality, if I have my queue always is full, why do I get unbounded response time? If you ask that question, then here is your answer. So if you have you actually can get unbounded response time with utilization 1. How that could happen? Well, let's say you get one request every 2 seconds and your service time is also 2 seconds. So what happens? Your utilization becomes 1. So 2 divided by 2, 1, and your system doesn't become unstable because you get one service, one request, and then you serve it. You get the second one, you serve it. You get the third one, you serve it. So every time it's just aligned when you're done with the previous one, and then you start the new one. Now, if you move to a random case where your inner arrivals are random, then things are a little bit different. What happens is that now, even if you get your utilization is less than 1, you get your arrivals in a random way, right? Let's say you have been processing the first one, and then so these faded rectangles are arrivals. So the second arrival comes here, the third arrival comes here, and then the fourth arrival comes here. And then you have this period of time here, because it was random, right? That your service is not utilized. And then let's say the fifth arrival comes here, again, sometime here that your system is not utilized. Now, this is a time that you cannot get back. So there was a time that there was no request in your system, so you could not possibly serve any request because there was no request in your system, and it happened because arrivals were random. So it just happened that you had like a long inner arrival time. So this time passed by and you didn't do anything. So now if your utilization is 1, your arrivals won't care about this. You're going to get this compensated in future with another arrival, but then you have already spent this time not doing anything, which you can't make up for. And this would mean that corresponding to this time that you spend not doing anything, a request will be queued. And as you get more and more of these times where you're idle because there are no arrivals, the length of your queue goes up and up and up and up. And that's basically why it's not sustainable to have utilization of 1 when you have random arrivals. Okay, I'm going to stop here. Thank you for everybody who attended the lecture. Be safe, take care, talk to you on Friday. Bye-bye.